This is Bob. Bob wants to send a message to his friend Alice, but the evil hacker Eve tries to intercept and read the message. To prevent this, Bob and Alice could agree upon a key to encrypt the message. But how is this possible without Eve also trying to intercept this key? One solution for this problem gives the so-called RSA algorithm, which is named after its developers Ron Rivest, Adi Shamir, and Leonard Adelman. The RSA algorithm is one of the oldest and most used public key algorithms for secure data transmission. The algorithm works with modular arithmetic and consists of a public and a private key. The strength of this algorithm comes from the fact that there is so far no efficient method that can disassemble large natural numbers in their prime factors. This video is structured into the 3 parts: preparation, encryption, and decryption. Firstly, Alice has to make some preparations to compute the private and public key. She chooses the 2 different prime numbers, P equals 7 and Q equals 5. In reality, these 2 prime numbers would be much higher to ensure a secure encryption, but for demonstration our numbers are easier to handle. After she picked the 2 prime numbers, she calculates P times Q, which is the number lowercase n, and after that P minus 1 times Q minus 1, which is the number uppercase N. The result for lowercase n is 35 and for uppercase N 24. Next, Alice chooses another natural number which greatest common divisor with the previously computed uppercase N is 1. In our case, this number could be 7. After that, she chooses another natural number x for which e times x is congruent to 1 modulo uppercase N. This mathematical expression means that e times x divided by uppercase N gives a remainder of 1. In our case, this number also can be 7. You can prove this by yourself by calculating e times x. This is 49. Then you divide this by uppercase N equals 24, which fits exactly 2 times in 49 and gives the expected remainder of 1. The pair of numbers x and e is Alice's private key, and it's only known to Alice herself. Finally, Alice sends the pair of numbers, lowercase n and e, unencrypted and freely accessible to Bob. This is the public key. In the next step, it's Bob's turn to encrypt his message. Therefore, he uses the public key Alice has sent to him. First, he chooses a number. This number represents the message and can be a letter from the alphabet. The number must meet with 2 criteria. Firstly, it has to be a natural number, and secondly, the number must be smaller than lowercase n. Bob chooses the number 2 as his message, which meets with both criteria. Now Bob calculates the number m dash. Therefore, he calculates m to the power of e, the first number from the public key, and this expression modulo lowercase n, the second number from the public key. With concrete numbers, this would be 2 to the power of 7 and this modulo 35. In other words, he computes the remainder of 128 divided by 35, which is 23. So, m dash equals 23, which Bob sends back to Alice. Finally, Alice has to decrypt Bob's message. In case you already forgot, his message is the number 2. To decrypt the message, Alice uses her private key. Firstly, she must calculate the number m double dash. Therefore, Alice needs the encrypted number m dash from Bob. With this number, she calculates m dash to the power of x, first number of the private key, and this expression modulo lowercase n, second number of the private key. As a result, we get 23 to the power of 7 modulo 35. In other words, 23 to the power of 7 divided by 35. The remainder of this division is 2, which is the exact message from Bob, and the RSA algorithm terminates. All in all, there is a receiver, in our case Alice, who computes a public and a private key. The transmitter of the message encrypts its message with the public key and sends it to the receiver. Finally, the receiver decrypts the message with its private key.